In today's video, we are discussing 9 very important system design concepts. Whether you are a seasoned software engineer or just starting out, understanding the system design concepts will help you develop robust, scalable, and reliable distributed systems. Especially in today's era of generative AI solutions helping us with the coding, focusing on the design concepts has never been this important. Not just that, better understanding of system design concepts will help you crack the system design interviews with confidence. So, this video is a must watch for every software engineer. Let's get started. What if your favorite apps like Netflix or Uber crashed every time too many people tried using them? Wouldn't that be a real disappointment? Scalability is a system's ability to cope with the increased workload or users without sacrificing performance or reliability. So, in this video, let's talk about scaling your apps and handle lots of users and data without any hiccups. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. Scalability is the foundation of modern distributed systems. In today's interconnected world, digital platforms often experience exponential growth in users, data volume, and workload. Scalable systems can seamlessly accommodate this growth without sacrificing performance or reliability and maintain a positive user experience. We all know that a positive user experience means a thriving business. Scalable systems utilize resources efficiently by allocating and reallocating resources based on demand. This optimization reduces operational costs and maximizes the return on investment in infrastructure. Scalability comes in two flavors: vertical scaling, where you upgrade a single machine, and horizontal scaling, where the load is spread across several machines. Let's discuss a few practical approaches to implement scalability, including vertical scaling and horizontal scaling. Vertical scaling is also called scaling up. To achieve vertical scaling, more resources are added to a single machine, like more CPU power or more RAM. Imagine adding more horsepower to your car by upgrading the engine. That's vertical scaling in action. It's simple and effective, but has its limits. After a certain point, you no longer can upgrade the engine. In horizontal scaling, the load is spread across multiple machines of the same or different capacities. It is like having multiple cars instead of just one for a group trip. Load balancing helps us achieve horizontal scaling. Load balancing distributes incoming requests across multiple servers, ensuring optimal performance and efficient resource usage. It's like having a traffic cop directing cars to the least congested lanes on the highway. Load balancers employ various algorithms such as round robin, least connections, or IP hash to distribute traffic effectively. Caching plays a crucial role in scaling a system. Caching involves storing frequently accessed data in high speed storage, such as memory or SSD, to reduce the latency and improve the performance. By caching the data near application or user, systems can serve requests faster and minimize the load on backend databases or services. Content delivery networks or CDNs exemplify caching on a global scale. CDNs cache static content at edge servers worldwide to deliver content with low latency to users across the globe. Caching is like having a pantry stocked with your favorite snacks. You can grab them quickly without having to run to the store every time. Database sharding is one another way to achieve horizontal scaling. It involves horizontally partitioning the data across multiple database instances or shards based on a predefined key or rule. Each shard operates independently, allowing the system to distribute the data storage and processing workload efficiently. Sharding enhances scalability and performance by enabling systems to handle large data sets and high transaction volumes. Imagine organizing your book collection by genre and distributing them across different bookshelves. Database sharding is like having multiple librarians managing different sections of the library. You can find books faster and accommodate more readers. Let's explore real world applications where scalability is implemented. Think about how smoothly Netflix streams your favorite shows, even during peak hours. That's because they use horizontal scaling and caching to handle millions of viewers without buffering or downtime. Ever wondered how Uber matches riders and drivers in real time, no matter where you are? It's thanks to their use of horizontal scaling and load balancing. Consider how Amazon manages to process millions of orders seamlessly, especially during the holiday season. They leverage a combination of a vertical and horizontal scaling, load balancing, and caching to deliver a stress free shopping experience to their customers. Scalability is the secret sauce behind every successful digital service. By adopting practical strategies like vertical and horizontal scaling, load balancing, caching, and database sharding, we can build systems that can handle exponential growth. So, whether launching a new app or simply ensuring existing services can handle whatever comes their way, scalability is the key to business success. If you found this video helpful, give us a thumbs up and subscribe to our channel for more such interesting topics. Do check out our other videos on software performance optimization case studies, coding, big data, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time. Before we get into the details, let me emphasize the importance of staying updated and continuously learning in the tech world. With new advancements and innovations emerging every day, it's crucial to keep honing our skills. Check the description box for some learning resources covering coding, system design, and advanced computer science concepts. Do you know how companies like Amazon, Netflix, and Google maintain reliability, availability, and scalability in their large distributed systems? Today, we are diving deep into the world of replication and its critical role in maintaining smooth operation of large distributed systems. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. Replication in distributed systems is all about creating and maintaining copies of data and resources across multiple nodes. Doing so enhances fault tolerance, improves performance, and boosts scalability. Let's understand what each of these mean. By replicating data across multiple nodes, systems can withstand individual node failures. This improves overall system reliability and availability even in the face of node failures. Replicating and locating data closer to users reduces access latency. This enhances overall performance and responsiveness of distributed applications. We have a separate video dedicated to the topic of software performance metrics. Please watch that to gain more insights. Scalability enables the systems to handle increasing workload and user traffic by distributing the data access and processing across multiple nodes. Please watch our video on scalability to learn more. Now, let's explore various replication types employed in distributed systems. In synchronous replication, data modifications are acknowledged only after they are successfully replicated to all designated replicas. This ensures consistency but may introduce latency and reduce availability. This replication type is ideal for scenarios requiring strict consistency guarantees, such as financial transactions or critical data updates. Asynchronous replication speeds up the response time by acknowledging the data changes before replicating them to all the replicas. However, this can lead to data consistency issues if a node fails. This replication is suitable for applications prioritizing performance and availability over strict consistency, such as content delivery networks or social media platforms. In leader follower replication, one node, the leader, handles all write operations, propagating changes to follower nodes asynchronously or synchronously. This model simplifies the consistency but may introduce bottlenecks and single points of failure. Leader follower replication is effective for systems with a clear distinction between read heavy and write heavy workloads. Multi leader replication allows multiple nodes to accept write operations independently propagating the changes to other nodes either synchronously or asynchronously. This approach improves scalability and performance, but requires a conflict resolution mechanisms to ensure consistency. Multi-leader replication approach is often employed in globally distributed systems for replication across distribution centers. In leaderless replication, all nodes are equal peers, accepting read and write operations independently. This model offers high availability and scalability, but requires consensus protocols to maintain consistency. Leaderless replication cannot be synchronous due to the inherent difficulties and compromises involved in achieving synchronous replication without a leader. Leaderless replication is recommended for highly scalable systems with decentralized architectures, where the emphasis is on fault tolerance and horizontal scalability. Amazon uses a combination of multi-leader and leader-follower replication strategies to ensure high availability and consistency across its globally distributed e-commerce platform. Meta utilizes leaderless replication techniques, enabling seamless interaction and content delivery for billions of users worldwide on its social media platform. Google employs a mix of synchronous and asynchronous replication approaches tailored to the specific requirements of its diverse portfolio of services, including Google Search and Google Cloud Platform. In conclusion, replication serves as the backbone of distributed systems, offering solutions to scalability, availability, and reliability challenges. By understanding how different replication methods work and where they are best used, organizations can design strong and effective distributed systems. If you found this video helpful, give us a thumbs up and subscribe to our channel for more such interesting topics. Do check out our other videos on software performance optimization case studies, coding, big data, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time. In this video, let's explore partitioning, the various partitioning techniques are used in distributed systems, and the benefits of partitioning. Partitioning in distributed systems involves dividing large data sets or workload into smaller partitions for better performance, availability, and scalability. What we call a partition here is called a shard in MongoDB and Elasticsearch. It is also known as a region in HBase, a tablet in Bigtable, a vnode in Cassandra and React, and a vbucket in Couchbase. So, not to get confused, they all mean the same. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. Let's dig deeper to understand the benefits of partitioning. Partitioning a data set distributes it across multiple nodes or machines in a distributed system. Each node handles a specific partition, enabling parallel processing. This boosts performance and reduces processing time. Partitioning helps evenly distribute the workload across the nodes in a distributed system. This load balancing approach ensures that no single node is overloaded while others are underutilized. This maximizes system performance and resource utilization. Partitioning lets a system scale horizontally. This enables the system to handle more data or users. To know more, watch our video on scalability. Partitioning provides a fault tolerance and high availability. Even if a portion of the system becomes unavailable, the remaining partitions and nodes can contribute to function, maintaining the overall system's availability. Partitioning can also be used to optimize the data locality, where data is stored and processed closer to the computing resources. Data locality minimizes the data transfer across the network, reducing latency and improving the overall system performance. Partitioning techniques vary based on the specific requirements and the characteristics of data and the distributed system being used. Let's discuss some of the common data partitioning techniques. There are two different types of data partitioning: vertical data partitioning and horizontal data partitioning. Vertical data partitioning, also known as column partitioning or column based partitioning, is a data partitioning technique where a table is divided vertically based on columns. In this approach, columns with similar characteristics or access patterns are grouped together in separate partitions. Normalization is one way to perform vertical partitioning. Let's consider an example of vertical partitioning in the context of an e-commerce application that manages customers' information. In a traditional table structure, you might have a single table called customers with columns such as customer ID, name, email, address, phone, and order history. All these columns are stored together for each row representing a customer. With vertical data partitioning, we can partition the table based on the logical relationships between columns. Let's say we decide to vertically partition the customers table into two partitions, personal info and order info. Vertical data partitioning is typically performed on user profile, product catalog, and customer related data in e commerce and patients' records and medical data in healthcare. In horizontal data partitioning, a table is split into smaller multiple tables, where each table contains a subset of the original table rows. These subsets are then placed on different nodes. Some of the popular horizontal data partitioning techniques are range partitioning, directory based partitioning, hash partitioning, and partitioning based on consistent hashing. We will be discussing each one of these in detail. So don't go anywhere and stay tuned. In range partitioning, data is divided into partitions based on a specific range criteria. Each partition then contains a predefined range of values. Let's consider an example of range partitioning in the context of a sales database. We have a table named sales data with columns order ID, order date, customer ID, product ID, and quantity. To apply range partitioning, we divide the sales data table based on the order date column, which shows when each order was placed. Here is how we split the data into three partitions. First partition, recent orders, containing the last 30 days orders. Second partition, historical orders, which contains orders from 31 to 365 days ago. And the third partition, archived orders, containing orders older than 365 days. Each order is stored in the partition that matches its order date. New orders go into the recent orders partition, and as time passes, orders move to different partitions based on how old they are. Google's Big Table and Apache HBase seem to leverage range partitioning. However, range partitioning has its limitations. In range partitioning, efficient range queries can only be done using the partition key, not other keys. Plus, if a big range spans multiple nodes, query performance suffers. Also, data distribution may be uneven if one range has more data than others. In directory-based sharding, the data items are distributed across the shards based on explicit mappings maintained by a centralized directory or metadata service. This approach is beneficial when there is a need for a centralized control over data distribution and routing in a distributed system. Consider an example of directory-based sharding in an e-commerce sales database. We have a distributed database storing sales orders across multiple shards. Instead of a predefined ranges, a central directory maps each order to a shard based on its ID. When accessing or modifying data, the directory routes a request to the correct shard. Directory-based sharding centralizes control over data distribution, but the directory becomes a single point of failure. Google's Spanner and Amazon's DynamoDB uses directory-based sharding. Hash partitioning divides the data into partitions using a hash function on a column. For example, Cassandra and MongoDB use MD5 as the hash function. Let's consider an example of a hash partitioning a customer database. We have a table called customers with the following columns: customer ID, name, email, and city. To apply hash partitioning, we partition the customers table based on the customer ID column. The partitioning process involves the following steps. First step, determine the number of partitions. Let's say we want 4 partitions. Then second step, define the hash function. Choose a hash function for the customer ID column. Lastly, apply the hash function to each customer ID. This way, each customer record gets assigned to a partition based on its hashed customer ID. Choosing the right partitioning key and hash function is vital in hash partitioning to ensure the data is distributed evenly. Constant hashing is a smart way to distribute data across many nodes without the need to move the data around when nodes are added or removed in the cluster. It works by using a hash function and a circular structure to assign data to partitions. Let's illustrate consistent hashing with an example of a distributed cache system. Suppose we have a distributed cache with four nodes A, B, C, and D. Each node represents a partition. The partitioning process involves assigning nodes, where we create a circular ring representing all possible hash values. Each node is placed multiple times on this ring based on its hash value. After that, mapping data. When storing or retrieving data, we hash its key to get a value. This value is then mapped onto the ring to find the corresponding node. Now, let's understand how the partitioning using a consistent hashing works when the cluster changes. That is, when we add or remove nodes from the cluster. If we add a new node like E, its positions on the ring are determined. We adjust the positions between existing nodes to balance the load, minimizing the data movement. If a node fails, like C, its keys are redistributed among other nodes. Only a fraction of keys need to be moved as other nodes take over some of the failed nodes' responsibilities. Consistent hashing is widely used in distributed systems like caches, databases, and CDNs. We have explored data partitioning, but how does a client find the right node to connect to for a request? Also, the allocation of partitions to nodes varies after rebalancing, which the client is unaware of. So, how does a client find the right node to connect to? This is called service discovery. There are a few methods to handle this. Let's discuss them. In one approach, clients can request any node. If it does not have the data, it forwards the request to the correct node. Another approach is using a routing tier. Requests are sent there first, which then directs them to the appropriate node. And the last approach is that the clients already know which partition is on which node and can connect directly. But keeping track of node changes is a challenge. Solutions like Zookeeper help manage these updates. We have a separate video explaining how Zookeeper manages Apache Kafka cluster. Please watch that to learn more. Sharding or partitioning helps systems scale and improve performance, but it adds complexity that may not always be necessary. Here are few alternate approaches. First approach, vertical scaling, where you upgrade single database server with more resources like CPUs, memory, and storage. This is easier to manage than sharding, yet allows a significant expansion. Second, SQL optimization, where SQL queries and database schema are fine-tuned for better performance. Third, caching. Employ in-memory caches such as Redis to lessen database load by avoiding frequent queries. And fourth approach, use combination of read replicas and load balancer. This offers a horizontal read scalability without full sharding complexity. Also, it distributes reads across replicas. In conclusion, partitioning optimizes distributed systems, performance, and scalability. Understanding options like range partitioning, directory based partitioning, hash partitioning, and consistent hashing enables architects to design robust distributed systems. If you found this video helpful, give us a thumbs up and subscribe to our channel for more such interesting topics. Do check out our other videos on software performance optimization case studies, coding, big data, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time. Did you know? Ticketmaster, a global ticketing platform, faced a significant challenge during the sale of Taylor Swift's The Eras Tour tickets. Their system, called Verified Fans, struggled to handle an overwhelming demand of over 14 million users. The system experienced cascading failures due to underpreparedness for the high volume of customers. Critical issues included passcode validation errors, prolonged wait times, and a failure to reject new requests after system capacity was exceeded. All these issues ultimately led to a disruptive and frustrating user experience. Whether you are a seasoned developer or new to performance monitoring, software performance metrics are vital to ensure your applications run efficiently and meet the user's expectations. In today's video, we will explore 10 key performance metrics that will help you assess and improve your software's performance. If you want to unlock your full potential, stay ahead of the competition, and achieve remarkable success as a software engineer, this video is a must watch for you. So don't miss out. Watch this video now and watch it till the end. Hello everyone, welcome to Tech and Career Bites. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product-based organization. So, are you ready to unlock the secrets of top-notch software performance? Let's dive in and explore those 10 key performance metrics that will help us succeed as a software engineer.
At number 10, response time. Response time is measured in seconds or milliseconds.
Imagine you're playing a game on your computer. Response time is the time it takes for your game character to move after you press a button. The faster the response time, the quicker your character moves in the game.
At number 9, CPU usage. CPU usage is measured as a percentage of CPU utilization. For example, 60% or 80% CPU utilization.
Think of the CPU as the brain of your computer. The CPU usage is how busy the brain is. If the brain is too busy, then it might slow down your computer. So we do not want the CPU usage to be too high.
At number 8 is memory usage. It is measured in megabytes or gigabytes.
Memory is a computer's short-term memory or RAM. If a program uses too much of memory, it is like taking up too much of space in the brain and it will slow down the computer.
At number 7 is network latency. Network latency is measured in milliseconds.
Network latency is like the time it takes for a message to travel from one computer to another computer over the network. But wait, is it not the same as response time? Not really, because response time includes not just the network latency, but also processing time, page load time, and page rendering time.
At number 6 is the error rate. Error rate is measured as a percentage of errors. For example, 2% error rate.
Errors are like mistakes in a computer game. If there are too many errors, then there are too many mistakes in your software application. We want as few errors as possible.
At number 5, mean time between failures or MTBF. MTBF is measured in hours.
Think of MTBF as how often your computer or game has problems. A long MTBF means your computer or game works very well for a long time before having any issues. Did you know AWS is designed and developed not to have more than 5 minutes and 26 seconds of downtime in a year? Keep watching the video till the end as we will be discussing an important metric around downtime and availability as a bonus.
Number 4, mean time to repair or MTTR. MTTR is measured in hours. For example, MTTR of 2 hours.
MTTR is like how fast someone can fix your computer or game when it has problems. A shorter MTTR means it can be fixed quickly. We want a shorter MTTR for the softwares that we are developing.
Number 3, throughput. Throughput is typically measured in bits per second or bytes per second.
Before discussing the throughput, let's first understand what the network bandwidth is. Network bandwidth is like how wide the road is for the data to travel quickly. A wider road allows more data to pass through, just like a bigger highway allows more cars. And throughput is the amount of data transmitted over the network in a given amount of time. It is typically measured in bits per second or bytes per second. As promised, let's discuss one another important metric, availability, as a bonus. Availability measures how consistently your application or software is operational and available to the users. We mentioned earlier that AWS is designed and developed not to have more than 5 minutes and 26 seconds of downtime in a year. Any guesses how the availability of AWS is expressed as a percentage of uptime? It is 99.999 percentage. That is 5 nines availability. AWS has 5 nines of availability.
At number 2, we have request rate. Request rate is measured as requests per second or RPS.
Request rate is how many tasks or requests your computer can handle in a second. The more the RPS, the better it is, as your computer can do multiple things at once.
And at number 1, we have the most important performance metric, concurrent connections.
Concurrent connections is like how many friends can play with you the game at the same time. The more concurrent connections, the more friends can join you in your game. In today's video, we discussed 10 key performance metrics. These performance metrics help software engineers develop software that runs smoothly, is fast, and has few problems as possible. If you like this video, then please do check out our other videos. Don't forget to like, comment this video, and subscribe to my channel. My name is Rupa, and I thank you so much for watching this video. See you in the next video. Are you someone involved in web development, API design, or working with web services? In that case, understanding HTTP actions or verbs is a must for you. In today's video, we will discuss top HTTP actions or verbs along with examples. HTTP verbs form the foundation of communication in web development and are essential for designing, consuming, and troubleshooting APIs and web services. They provide a standard way to express the intended action on the resources over the web. This is really an interesting topic, so watch the video till the end. Hello everyone, welcome to Tech and Career Bites. I'm a software professional with more than 20 years of experience, including 7 years in leadership roles at a global product-based organization. HTTP stands for Hypertext Transfer Protocol. This is an application layer protocol that facilitates data transfer and communication on the World Wide Web. HTTP actions, also referred as HTTP methods or HTTP verbs, are the commands used in Hypertext Transfer Protocol to specify the desired action on a resource. These actions define how the client and server should interact with the identified resource. There are several HTTP verbs available. Let's discuss the frequently used along with examples. Let's first discuss HTTP GET verb. HTTP GET request retrieves a resource from the server. It is idempotent in nature, which means multiple identical GET requests return the same result. For example, consider a HTTP GET request to retrieve the product's details. The response from the server will be a JSON object with an array of products. HTTP put updates or creates a resource on the server. It is also idempotent with multiple identical put requests updating the same resource. For example, consider this put request to update the user details for the user with ID 123. If the user does not exist, then the put request creates that resource on the server. The response from the server will be a JSON object with updated user information. HTTP post is used to create new resources on the server. It is not an idempotent action. That means if there are multiple identical post requests, then it will end up creating duplicate resources on the server. For example, consider this post request to create an order on the server. The response from the server will be a JSON object with the details of the order created. Let's discuss HTTP delete verb. HTTP delete request deletes a resource on the server. It is an idempotent action. That means multiple identical requests impacts the same resource. That is, the same resource, if it exists, it's deleted. For example, consider the delete request to delete a product with ID 789. The response from the server will only indicate a success or failure and will not have any content in the response body. The patch request is used to apply partial modifications to the resource on the server. It is again an idempotent action. For example, consider the patch request to partially modify the user with the ID 456. The response from the server will be a JSON object with the updated user information. HTTP head method is used to retrieve the headers of a resource without the actual response body. For example, consider the HTTP head request to retrieve the headers of the document with ID 789. As the response will only have the headers information, the response from the server is typically minimal. The HTTP options describes the communication options for the specified resource. The response from the server typically includes information on allowed methods, headers, and other potential capabilities for the specified resource. The HTTP trace method is used to perform a message loopback test. It is typically used for diagnostic purposes, allowing the client to see the modifications done by the intermediate servers. In today's video, we discussed frequently used HTTP actions or HTTP verbs. I hope you learned something useful today. If you liked this video, then do check out our other videos. Also, don't forget to like, comment this video and subscribe to my channel. My name is Rupa and I thank you so much for watching this video. See you in the next video. Understanding data fetch patterns is crucial for developers who are involved in building real-time applications, web applications, or systems with dynamic data requirements. It helps the developers make informed decisions about the design and architecture of the systems. And we all know that a well-architected system contributes immensely to the user satisfaction and success of the application. Data communication between a client and a server can occur through various protocols and mechanisms, each serving its specific purpose. If you remember, in our previous video, we discussed various HTTP actions used for web communication and data transfer. If you have not yet watched that video, I strongly recommend you watch that video now. And in today's video, we will focus on data communication or data fetch mechanisms between a client and server using HTTP protocol. So let's dive in. Hello everyone, welcome to Tech and Career Bites. I'm a software professional with more than 20 years of experience, including 7 years in leadership roles at a global product-based organization. A data fetch, as you rightly guessed, is a process of retrieving a data or information from a source, typically a server or a database, and then bringing it to an application or client for further processing or display. In applications with high read throughput, such as Quora or Twitter, with millions of data fetch requests every second, the need for an effective communication structure becomes very crucial. Let's discuss our first data fetch pattern, data polling. With the data polling, the client repeatedly requests the server for updates or new information. There are two techniques in data polling, long polling and short polling. In short polling, the client sends a request to the server at predefined intervals, usually less than a minute, asking for updates of the latest information. The server receives the request and processes it. If there is new information, the server responds to the client with the updated data. And if there is no new data, the server may respond with an empty message. The client repeats this process at regular intervals, regardless of whether there is new data or not. As you can see in the figure, even though the update is available, the client requests only at the specified interval, thereby delaying the data retrieval. Short polling works well when the information availability time frame is known well in advance so that the polling frequency can be set accurately. If the polling frequency is not accurate, then it has drawbacks like unnecessary requests to the server when the updates are not available or delayed data retrieval when the updates are available at the server but the client has not requested. Let's now discuss our second data polling technique, long polling. Long polling operates similar to short polling, but the client stays connected and waits for a response from the server until new updates are available or a timeout occurs. This approach minimizes idle time, but it introduces connection management challenges. Clients may need to reconnect multiple times after timeouts to get new data. Using WebSockets is one another way of data communication between a client and a server. WebSocket is a persistent full duplex communication protocol running on a single TCP connection. The process of establishing a WebSocket connection often involves an initial HTTP handshake over TCP, and then the connection is upgraded to the WebSocket protocol. WebSocket frames are more lightweight than the traditional HTTP requests, and they support full duplex communication, meaning both the client and the server can send messages to each other. WebSockets addresses the limitations of data polling techniques, enabling real-time communication between the client and the server without the need for continuous polling. They are suitable for scenarios requiring low latency and high resource utilization. Let's compare the three approaches we just discussed. You can pause the video and think if this comparison makes sense based on what we learned so far. If there is anything you would like to discuss further, leave your thoughts in the comment section and I will get back to you. In today's video, we discussed data fetch or data retrieval patterns based on HTTP request and response. If you like this video, do check out our other videos. Also, don't forget to comment this video and subscribe to my channel. My name is Rupa and I thank you so much for watching this video. See you in the next video. So, how is it going so far? Lot of learning, isn't it? If you have any suggestions or questions, share it in the comment section. I will get back to you as soon as I can. As you browse through your favorite Netflix shows, you might have noticed the curated recommendations. Have you ever wondered how Netflix shares these personalized recommendations to you? Let's find out. In today's video, we will discuss essential protocols like webhooks, server-sent events, Websockets, and WebSub widely used in event-driven architecture. If you are someone involved in API or web development, then understanding event-driven architecture and these protocols is very crucial. So don't miss out on valuable insights. Watch this video till the end. Hello everyone, welcome to Tech and Career Bites. I'm a software professional with more than 20 years of experience, including 7 years in leadership roles at a global product-based organization. HTTP request response based data fetch mechanisms involve continuous requests or open connections as seen in short pooling and long pooling respectively. We have discussed these mechanisms at length in our previous video. If not watched, then I suggest you watch that video. The link is available in the description box also. Event-driven architecture takes a different approach by allowing systems to react to events as they occur. This promotes a more efficient, scalable, and real-time communication model. Netflix utilizes an event-driven approach for managing its recommendation system. Events such as user interactions and viewing history trigger recommendations in real time. Event-driven architecture comprises several key components that collaborate to create a responsive and event-driven system. These components include event producers, event consumers, event bus, and event store. Event producers are the entities responsible for generating events based on changes or triggers within the system. Event consumers are the components designed to react to specific events by initiating predefined actions or processes. Event bus is the communication channel that facilitates the flow of events between producers and the consumers. It acts as a mediator, ensuring seamless event distribution. Event store is a repository that records and manages a historical log of events, providing a valuable resource for auditing, debugging, and system analysis. Let's discuss some widely used protocols in event-driven architecture.
First protocol, webhooks.
Webhook is a one-way, event-driven communication protocol based on HTTP. It enables applications to send real-time information when particular events get triggered. In a webhook protocol, the consumer first subscribes to a particular topic with the producer. After the subscription, the producer automatically notifies the consumer when new events occur. It is important to note that the webhook protocol is usually used when server to server or application to application real-time communication is required. Let's understand how it works with an example. Suppose you have a continuous integration system or a deployment pipeline and you want to receive real-time updates whenever certain events like a code push, pull request or any issues occur in your GitHub repository. In this scenario, you can use webhooks to establish communication between GitHub and your CI/CD system.
Second protocol, server sent events or SSE.
Server-sent events are unidirectional server-to-client server push approach and are part of HTML5 specification. In server-sent events, communication is initiated by the client. To establish a connection for receiving events, the client makes a request to a specific URL. This is typically done using a JavaScript API called event source. When making the request, the client specifies the content type it can handle as text event stream. This is done through the HTTP accept header. SSE approach is mainly used for the notification system, where clients get notified by the server upon update. Twitter, Instagram, and Meta are using SSE for real-time newsfeed updates. It's important to note that server-sent events supports only text-based streaming, making it unsuitable for audio or video streaming.
Third protocol, WebSub.
WebSub presents an event-driven architecture approach for distributed publisher-subscriber communication. Its core components include a publisher, hub, and a subscriber. A hub acts as an intermediary or a middleman in the communication flow between publishers and subscribers. It facilitates the distribution of content from publishers to the subscribers and decouples publishers and subscribers, ensuring seamless content delivery. One example of a hub is the Google's product Pub Sub Hub Bub, or also called Push Hub. WebSub facilitates multiple clients receiving updates from the same producers with built-in security features. It is specifically tailored for scenarios where timely updates to web content, such as blog posts or news articles, are essential. It is commonly used in content distribution and syndication.
Fourth and the last protocol, WebSockets.
WebSocket protocol enables bidirectional communication between the clients and the servers. We have discussed WebSocket at length in our previous video. I suggest you watch that. In this video, we discussed protocols used in event-driven architecture. The choice of protocol depends on the specific communication needs of your application. Each protocol has its own unique attributes. SSE is suitable for text payloads to clients, WebSub excels in scenarios involving both clients and servers, and WebSocket enables unrestricted bidirectional communication. Understanding these protocols empowers developers to select the most suitable approach for efficient and real-time communication in diverse applications. If you liked this video, then do check out our other videos. Don't forget to like, comment this video and subscribe to my channel. My name is Rupa and I thank you so much for watching this video. See you in the next video. Today, we will explore the CAP theorem, strong and eventual consistency, and the PACLC theorem with some real-world examples. The CAP theorem states that in the design of a distributed system, it is impossible to guarantee all the three properties, consistency, availability, and partition tolerance simultaneously. But do you know that this statement is misleading? That's right, it is misleading. Let's discuss that in detail and understand why we are saying it is misleading. Hi there, welcome to Tech and Career Points. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. Let's first understand the three properties: consistency, availability, and partition tolerance. Consistency ensures all nodes in a distributed system see the same data simultaneously. This is crucial for data integrity. Availability means every request gets a response, regardless of node failures or network partitions. And partition tolerance allows the system to function despite network issues. Network partition happens when the nodes lose connection, causing them to split into separate groups that can't share any data. In any distributed system, network partitions are inevitable. Whether we like it or not, they will happen. When the network is functioning correctly, the system can provide both consistency and availability. And when the network partition happens, we must choose either consistency or availability. Thus, a better way of phrasing the CAP theorem would be consistent or available when the network is partitioned. A system can either be consistent or available when the network is partitioned. That makes sense, right? Now, if a system chooses a consistency over availability, it means that it prioritizes maintaining a consistent view of the data and may sacrifice availability during network partitions. This is because when the communication between nodes fail, the data in each of these nodes may become out of sync. One or more nodes may have latest data while the other may have stale data. In this case, as we do not want to compromise on the data consistency, the system may refuse to respond to requests until consistency is restored, thereby compromising system availability. Let's understand this better with a real world example. Think of a bank where having the right account balance is really important. If a user withdraws money from an ATM and the transaction gets recorded on one part of the system but not on another because of a problem, the user might see different account balances when checking their balance. This is not a good experience, isn't it? The user may panic. To avoid this, during a network partition, if a user tries to withdraw funds, the system might temporarily reject the transaction until the connection is restored. If a system chooses availability over consistency, it means that it prioritizes remaining responsive and available even during network partitions, but may compromise strong consistency guarantees. In this situation, the system might temporarily allow different or conflicting data states until the consistency is restored. Think about Ola and Uber. They focus on being available so that the users can book the rides easily and the drivers can accept those requests, even in areas with bad internet. During a network problem, if a driver accepts a ride but loses connection before confirming, the system might let them accept another ride to keep the service going. This could cause issues like double bookings or conflicting ride statuses until the connection is fixed. Even with these problems, the priority is keeping the service available for users without interruptions. A distributed system prioritizing consistency over availability offers strong consistency, and a system that prioritizes availability over consistency offers eventual consistency. Let's dive deeper into these two consistency models, strong consistency and eventual consistency. In a system that guarantees a strong consistency, every node in the system sees the same data at the same time, regardless of where the data is accessed. Achieving strong consistency often requires synchronous replication and coordination among nodes. Synchronous replication and coordination among nodes results in increased latency and decreased availability during network partitions. To know more, watch our video on replication. Eventual consistency is less strict than strong consistency and allows the temporary inconsistencies during asynchronous updates across nodes. This approach focuses on keeping the system available and working even if there are network problems. As we discussed earlier, applications that prioritize the data integrity and transactional correctness, such as financial systems, may opt for strong consistency despite potential availability trade offs. On the other hand, applications like Uber or Ola may prioritize availability and responsiveness over strict consistency, making eventual consistency a more suitable choice. Just because the CAP theorem says either consistent or available does not mean we can't achieve both consistency and availability. Confusing, right? Let's discuss. By focusing on scaling up data centers vertically instead of spreading them out horizontally, we can have both consistency and availability. But the system won't be truly distributed anymore. Since network partitions are unavoidable in distributed systems, it's crucial to decide on the right balance between consistency and availability. Google's spanner database seems to be an exception, though, violating the CAP theorem. How? Let's understand that. Google's spanner database system is an interesting case study when it comes to the CAP theorem. It aims to provide high availability and partition tolerance while maintaining a strong consistency across its geographically distributed data centers. It achieves this by implementing a unique architecture and leveraging a synchronously replicated data across multiple data centers. Now, let's discuss the PACLC theorem. The PACLC theorem is an extension to the CAP theorem. The PACLC theorem states that during network partitions, a distributed system must choose between availability and consistency as per the CAP theorem. Else, when the system is functioning normally without partitions, it must choose between latency and consistency. When consistency is prioritized in the absence of network partition, latency tends to suffer because ensuring consistency often requires a synchronous replication and coordination among nodes, which can increase the time it takes for operations to complete. To know more about synchronous replication and its impact on availability, watch our video on replication. In conclusion, understanding the CAP theorem and PACLC theorem helps system designers make informed decisions, ensuring the creation of robust and resilient distributed systems. What will you prioritize in your next project? Consistency or availability? Do let me know in the comment section. If you found this video helpful, give us a thumbs up and subscribe to our channel for more interesting tech topics. Also, do check out our other videos on software performance optimization case studies, system design, big data, coding, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time. Annoyed by slow loading websites during busy times? Frustrating, isn't it? Well, there is a secret weapon companies use to stay speedy: caching. In today's video, we are going to cover almost everything about caching, including its benefits, caching strategies, cache invalidation methods, cache eviction policies, and solutions to some common cache related problems. It's going to be a lot of learning and fun learning. So keep watching till the end. Hi there, welcome to Tech and Career Bites. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. In today's world, users expect lightning fast website, but as the traffic peaks, the performance can suffer, and that's where caching comes in. Consider a popular e-commerce platform experiencing a surge in user traffic during a festive season sale. As the number of users increase, so does the volume of database queries, resulting in sluggish performance and delayed response times. This performance degradation impacts the user experience and may lead to lost sales opportunities for the business. To mitigate the performance issues caused by increased database queries, the e-commerce platform decides to implement caching. By caching frequently accessed information such as product details, prices, and availability, the platform aims to reduce the database queries and deliver faster response time to users browsing the website or making purchases. But will the caching really help the e-commerce platform mitigate the performance issue? Let's understand how caching works. When a user visits the e-commerce platform to view product listings, the system first checks the cache for the requested product information. If the data is found in the cache, it is retrieved quickly and served to the user, resulting in a seamless browsing experience. However, if the data is not present in the cache, the system retrieves the information from the database, serves it to the user, and updates the cache to prevent future incidents of not finding the data in the cache. If the data is found in the cache, it is called cache hit, and if not, it is called cache miss. But how does the desired data get loaded to the cache? And how do we ensure synchronization between the cache and the database? There are several caching strategies that help us keep the data in sync. Let's explore them. Caching strategies are the approaches to manage how data is stored and retrieved in a cache. Let's understand few commonly used caching strategies. In a read-through caching approach, when a cache miss occurs, the system automatically fetches the data from the database, updates the cache, and returns the data to the user. Using memcached for caching of frequently accessed database queries in a web application is an example of read-through cache. In cache-aside caching, when a cache miss occurs, the application directly fetches the data from the database, updates the cache, and returns the result to the user. MongoDB caching Frequently accessed user profiles in a social media platform is an example of this caching. With write back caching, data is written to the cache first and then asynchronously returned to the underlying storage at a later time. This strategy improves write performance by reducing the latency associated with synchronous disk writes. A database system caching write operations in memory before committing them to disk to improve overall system responsiveness and throughput is an example of this caching. In write-aside caching strategy, the data is directly written to the underlying storage without being cached initially. Only subsequent read requests for the same data trigger caching. This approach is beneficial for data with low access frequency or data that does not benefit from caching. An example of this caching would be a file storage system where large files are written directly to disk without being cached to optimize cache utilization for frequently accessed files. In write through cache, every write operation to the database is also written to the cache simultaneously. This ensures that the cache is always up to date with the latest data. Redis cache with write through caching for user session management is an example of this. Okay, now that we have loaded the data in the cache, how do we ensure that it is still valid and not outdated? Cache invalidation methods confirm that the cached data is in sync with the original source. Cache invalidation is the process of removing or updating the cache data when it becomes outdated. This ensures the accuracy of the cache data. Cache invalidation methods are broadly classified into two: time based invalidation and event based invalidation. Let's understand each of them in detail. Time to live expiration is a time based invalidation method. This method involves setting a time to live value for cached content, after which the content is considered stale and must be refreshed. When a request is received for the content, the cache checks the time to live value and serves the cached content only if the value has not expired. If the value has expired, the cache fetches the latest version of the content from the origin server and caches it. For example, in a news application, articles in the cache may have a TTL of 24 hours. After 24 hours, the articles expire and are removed from the cache. In event-based invalidation, the cached entries are invalidated based on specific events or triggers, such as data updates or deletions. Let's discuss some commonly used event-based invalidation methods. The purge method removes the cached content for a specific object, URL, or a set of URLs. It is typically used when there is a change or update to the content and the cached version is no longer valid. When a purge request arrives, the cached content is removed immediately, and the next request for the content will be served directly from the origin server. Refresh method fetches a requested content from the origin server even if cached content is available. When a refresh request is received, the cached content is updated with the latest version from the origin server, ensuring that the content is up to date. Unlike a purge, a refresh request does not remove the existing cached content. Instead, it updates it with the latest version. The ban method invalidates the cached content based on a specific criteria, such as a URL pattern or a header. When a ban request is received, any cached content that matches the specified criteria is immediately removed, and any subsequent request for the content are served directly from the origin server. Stale while revalidate method is used in web browsers and CDNs to serve stale content from the cache while the content is being updated in the background. When a request is received for a piece of content, the cached version is immediately served to the user and an asynchronous request is made to the origin server to fetch the latest version of the content. Once the latest version is available, the cached version is updated. This method ensures that the user is always served content quickly, even if the cached version is slightly outdated. After the cache invalidation, it appears that the cache is full and has latest data. But the cache misses have increased tremendously. So, what steps should be taken next? We need to make room for new entries in the cache and reduce cache misses. This process, known as cache eviction, is crucial for optimizing the cache performance. Cache eviction policies determine which items are selected for removal based on a certain criteria. Let's discuss few cache eviction policies. LRU removes the least recently accessed items when space is needed for new entries. For instance, in a web browser's cache using LRU, if the cache is full and a user visits a new web page, the least recently accessed page is removed to make room for the new one. MRU evicts the most recently accessed items to free up space when necessary. For instance, in a mobile app cache, when the cache is full and the user tries to access a new feature, the most recently accessed feature is evicted to accommodate the new data. In a first in first out cache, the oldest items are removed first when space is required. For example, in a messaging app, when the cache is full and a new message arrives, the oldest message in the cache is evicted. Least frequently used caching removes items that are accessed the least frequently. LFU keeps track of access frequency, and when space is limited, it removes items with the lowest access count. For example, in a search engine cache, less frequently searched queries may be evicted to make room for popular ones. Random replacement caching selects items for eviction without considering access patterns. For instance, in a gaming app cache, when new game assets are to be cached, RR randomly selects existing assets to replace. Each cache eviction policy has its advantages and disadvantages, and the choice depends on factors such as applications, access patterns, memory constraints, and performance requirements. The e-commerce platform in our example has now implemented a caching solution, leading to noticeable improvement in website performance. However, several cache-related issues have recently emerged. Cache-related problems occur due to issues such as multiple users or processors accessing data simultaneously, outdated cached data, limited cache size, network problems, incorrect cache configurations, implementation errors, dependencies on external systems, and inadequate cache forming strategies. Let's discuss solutions to few common cache related problems. Thunderbird problem occurs when multiple requests trigger simultaneously cache misses. This could happen when a large number of cached content expires at the same time. As the requests now directly hit the database, it overloads the database. There are two ways to mitigate this issue. One is to avoid setting the same expiry time for the keys. Another approach is to limit database access to essential business data only, preventing non essential data from accessing the database until the cache is operational again. Cache penetration happens when malicious users bombard the system with requests for non existent data. This causes a cache bypass and causes unnecessary load on the back end. One solution could be to implement input validation and rate limiting to mitigate the impact of cache penetration attacks on the system. The cache breakdown problem is similar to the Thunderhead problem. It happens when a hotkey expires. A large number of requests then directly hit the database, overwhelming the system. Since hotkeys make up 80% of the queries, a solution to this problem is not to set an expiration time for them. Cache crash happens when the cache is down, either due to software bugs or hardware failures, and all the requests directly go to the database. There are two ways to solve this problem. One is to set up a circuit breaker, and when the cache is down, the application services cannot visit the cache or the database. The other is to set up a cluster for the cache to improve cache availability. In companies like Amazon, Netflix, Google, Meta, and eBay, caching solutions like Redis and Memcached are usually used for caching dynamic data, and CDNs are usually employed for caching static content. In summary, caching is vital for optimizing the system performance in high traffic environments. I hope today's discussion will help you implement the right caching solution. If you found this video helpful, give us a thumbs up and subscribe to our channel for more interesting tech topics. Also, do check out our other videos on software performance optimization case studies, system design, big data, coding, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time.